Yes, sir, audible. Good
Okay,
afternoon, sir.
good afternoon. Uh, Share and then this slide. Okay. Now, unfortunately, again today there is a meeting at 4 o'clock. I will take the class for 1 hour. We'll definitely cover up the syllabus during the later part. Today also I have some other guest in the ISR. So I will take 1 hour class. So I will go little quickly today, just to uh, cover as much as possible. Okay. Remember, we started with. Is this slide visible?
Yes, sir.
Yeah. So we started with carbohydrates, and initially it was the named as hydrates of carbon. Then they found that there are many molecules which do not conform to this formula H2O M. This formula does not fit to many carbohydrates. Actually, carbohydrates are what? Final definition is polyhydroxy aldehyde or
স্যার
ketone. Yes.
স্যার আমি সৌরভ বলছি স্যার।
হ্যাঁ বলো।
স্যার আমি অ্যাকচুয়ালি কানেক্ট করতে পারছি না, বাট আমি শুনছি স্যার আপনার ক্লাস আছে।
তুমি কানেক্ট করতে পারছো না
না স্যার।
কেন গো?
স্যার অ্যাকচুয়ালি I have not been added to the team yet.
Oh, should I add now? Is it possible to add,
Sir,
or
it is
it is?
possible. So you can add later, sir. For the time being, I'm listening.
You are listening.
Yes, sir.
You are able to listen, right? So I can add
Yes.
later. Otherwise, I think I have to go out of this and then add. Or you can
Yes,
send
sir.
me
That's why I'm saying.
you can send me a request whether I can add here. I don't know whether it comes or not.
Actually, at the moment, I'm not able to do that, sir, because
Oh,
network
okay.
issue.
So should I start then continue?
Yes, yes, sir. You can continue.
Okay, so polyhydroxyaldehyde or ketone, that is the definition, and it starts with carbon number 3, where the simplest one was the glyceraldehyde. And there are two forms of glyceraldehyde because there is one asymmetric center, and the other one is this. Of course, at the same time, you can have the ketone also, because it says polyhydroxyaldehyde or ketone. So you can have a ketone functionality in the middle, but that is only one possibility. This is dihydroxyacetone, dihydroxyacetone. This is glyceraldehyde. I told you that this is D because of this presence. Fisher assumed, Emil Fisher, who was handling the structural elucidation, he assumed that the wedge to the left is called L and wedge to the right is called D, provided you write the Fisher projection in the correct order. The correct order is the top carbon should contain the number 1 carbon in the IUPAC system. Okay. So this was the starting point. Now, in your syllabus, it basically, you need to know the structure of glucose. That is the most common sugar of all. Okay. Now, glucose, its molecular formula can be determined by percentage composition, by traditional method. Okay, so people found that it has got the C6H12O6. Usually what is done for structure elucidation, they first go for the formula and then functional group. Functional group. So they found that it reacts with acetic anhydride, 5 acetic anhydride. So there are 5 hydroxy groups. Okay, because pentaacetate it forms. If there is, today I'll be little fast. If there is any problem, you can stop me also, raise question. Okay, so glucose contains 5 hydroxy groups. Glucose contains a carbonyl group because it reacts with one equivalent of phenyl hydrazine to form phenyl hydrazone. It reduces Fellings or Tollens solution. Fellings or Tollens, which is a classical test for aldehyde. But you must know that it is not only the test for aldehyde, but it is also test for any alpha hydroxy, where when there is a hydroxy group present attached to a ketocarbonyl, aldehyde will definitely reduce the Fellings solution or Tollens reagent, but alpha hydroxy, CH2OH. Alpha hydroxy carbonyls are also able to do the same thing, Felling or Tollens. Okay, so these reactions, Felling or Tollens, cannot tell you whether it is aldehyde or ketone. It also tells either CHO or CHOH. Okay, so it doesn't solve the issue, aldehyde or ketone. The important reaction is bromine water. If you add bromine water, then it's only the aldehyde group which is oxidized and not the ketone. And bromine water gave a compound where CO2H and then CHOH. There are 4 here, and then this is CH2H. So you get what is called glucaric acid. Sorry, gluconic acid. Gluconic acid, this one. Okay. It is only the characteristic of aldehyde, because you know aldehydes on oxidation gives the acid without losing any carbon. Okay, glucose contains 6 carbons, this acid contains 6 carbons. So it must be containing aldehyde moiety. If you use a strong oxidizing agent, a little stronger, like nitric acid, then your aldehyde is oxidized and the primary alcohol is also oxidized. So that means you get a dicarboxylic acid. In between there is this CHOH, 4 CHOH groups. 4 CHOH groups. Okay. So from these reactions, what you have got, glucose has 5 hydroxy groups, and it has got an aldehyde group. It has got a primary hydroxyl group. Okay. Up to that point, you know from these structures. But the problem is now 6 carbons can be attached in various ways. Like it could be linear or it could be branched. No? There are several possibilities. There is no it's a huge number. Permutation combination will give you. This is 5 carbon, 6 carbon. So it is just, these are 2 examples. So other structures you can always write. So the skeleton. So what is the skeleton of glucose? Whether the 6 carbons are really present in a linear chain or a branched chain. For that, one reaction was done. That is CHO. Right now, I am not giving the stereochemistry here. These are all stereogenic centers. So what reaction was done? That it was added HCN was added, and it becomes CHCN. Okay, and then OH, the cyanohydrin, and then CHOH. I can just write 4, and then CH2OH. Okay, so this is cyanohydrin. And then you can hydrolyze the cyanohydrin to carboxylic acids. So that will be CHOH, CO2H, and then CHOH, 4, and then CH2OH. Now you can do a reaction by which you can remove the reduce the hydroxy groups into H. That is by HI rate phosphorus. If you do HI rate phosphorus, so what will happen? You get CH2 will become CH3. So after that, the CHOH becomes CH2. Then this CH2OH becomes CH2. Then another CH2. I'm going from bottom. So there are 4 CHOHs. So 4 CH2s are there. Actually, then there are another one, this one. So that is also CH2. And you get this. So this is what? This is heptanoic acid. In heptanoic acid. So if N-heptanoic acid is obtained, just a second. Let me just check one. Gluconic acid, pentacetate. Yes, heptanoic acid, HI, heat. So N-heptanoic acid is obtained. What does it mean? It means that is a known compound. N-heptanoic acid is a known compound, is a known compound. So what will happen? That you can tell that all the carbons in glucose are then linearly placed, because you don't get any branched 7 carbon acid. Okay, so this is a linear acid. That means in glucose all carbons are linear, or if glucose is a straight chain molecule. Okay. So you can now write the structure of glucose. Not the structure, at least the constitution, because there are so many asymmetric centers, 1, 2, 3, 4, and CH2OH. So up to this point, you can write about glucose, but then you really don't know where are these OHs. How many possibilities are there? There are 2 to the power 4. That means 16 possibilities for only plus. That is the natural glucose, which you are obtaining from nature. So you cannot write the structure because you don't know the stereochemistry now. So that has to be found out. What is the stereochemistry of these carbons? Whether the weight is on the right or left, whatever it is. So that's a tremendous task. Okay. And in order to, so 16 possibilities, what Fisher assumed one thing I was telling last time to you also. Fisher assumed that this is number 1 carbon, 2, 3, 4, 5, 6. Fisher assumed that this plus glucose has D configuration. Okay. So that reduces the number of possibilities. Number of possibilities means either these 3 OHs are on the right, or this OH is on the left, these 2 are on the right. At least it reduces immediately to 8 possibilities. Because the last one you fixed. There is no rationale for this. There is no justification for this. It is just for his convenience. He thought that this naturally occurring glucose belongs to the D series. So he classified carbohydrates as 2 kinds of series. One is the D series, another is the L series. L series is where it is on the left. Okay. So if plus glucose ultimately was shown to know it is not belonging to the D series, then you have to just write the mirror image to make the L series. Okay. But anyway, he started by assuming that this is the D series. Okay. Now the question is how to determine these three configurations, 2, 3, and 4. Now at that time there were some aldopentoses. Aldopentoses were known. What is aldopentose? This is 5 carbon. No? Aldopentose is CHO, then CHOH, then CHOH, then CHOH, then CH2H. This is aldopentose. How many aldopentoses are possible? Now there are 3 asymmetric centers. So 16 to the power, sorry, 8 to the power 3, 8 possibilities. That means it can exist in 4 DL pairs. Let me see whether I have the names of these. Names of these and aldopentose. They started with an aldopentose, an example of 6. So, and Fisher again thought that these aldopentoses which are naturally occurring, one of them is called minus, means the names are minus arabinose is one. Another was, some names I remember, one is minus arabinose, and another is ribose. Another is lixose, so far as I remember, lixose and xylose. Anybody has the internet connection and mobile? I also have. The names are sometimes confusing. I think these 4 are there. Let me see. Have a quick check. Aldopentose. Names of the aldopentose. Names. Are you trying? Aldopentose. Names of the aldopentoses. Very slow. Did you get any? It is not slow. Aldopentose. Your mobile data is very slow. No data connection. Could you get the names?
Yes, sir.
Yeah, what are the names? Arabinose is one.
Yes, mannose, ribose, xylose.
No, mannose is 6. Arabinose, then ribose is there. What is the sign? The rotation sign plus for ribose. See, rotation is also, sign is important. Aldopentose. Xylose should be 1. That's correct. Yes, it's a pentose. What are the names? What is the example of aldopentose? Mine is very slow. Otherwise, very slow. Yeah, maybe now it is.
Xylose and lysose is there.
Xylose, lixose, is it? That is lixose. It should not be. Okay. Yeah, now I got some of the structures. Yeah, one is ribose. Okay, that is correct. The other is arabinose. That is also correct. Third one is xylose, correct. Lixose. Yeah, all are correct. Only I am little bit only concerned with the with this optical rotation, because we are only handling only the naturally occurring, that this slide does not tell. It says 8 possibilities, and but what is their rotation? D-ribose, D-arabinose, D-xylose, D. We may skip that. That will not hamper our, but should have been written that what is their sign of rotation. Because each compound can exist in 2 forms, plus and minus. Both are ribose. So what is the naturally and the carbon? It doesn't say the rotation. That is too bad. Natural isomer, D-erythrose, we can conclude. Example of D-aldopentose. Okay, let us not very worried about this rotation. Just think that at least arabinose we know that it is occurring in minus form, levorotatory. Okay. Now, if arabinose also had the same type of property like glucose, means arabinose only except one hydroxy carbon is less. So if you do the same type of experiments with arabinose, like if you add acetic anhydride, now you get tetraacetate. So that will show you that there are 4 hydroxy groups. If you add bromine water, you get again the 5 carbon acid, CHOH, 3 CH2H. So it is the same, same type of chemistry. Only difference between glucose and arabinose is that it contains 5 carbons, glucose contains 6 carbons. Okay. Now, if you look at what could be the structure of arabinose, we only know that arabinose has an aldehyde, because with bromine water, it gives free acid without any loss of carbon. And with acetic anhydride, it gives a tetraacetate. Okay, and then the same experiment. How do you know all the 4 carbons are in the linear chain? You add HCN, so it goes to cyanohydrine, hydrolyze, it goes to the hydroxy acid, and then HI, red phosphorus, will give you, in this case, hexanoic acid. So straight chain hexanoic acid. That proves that it is in the straight chain. So that is okay. Now, Fisher assumed that again arabinose minus arabinose is belonging to the D configuration. If minus arabinose belongs to the D configuration, then how many you can draw? How many structures you can draw for arabinose, keeping this as on the right side. So always this is D. Don't change that part. So what you change is the upper part, the configuration of the upper part you change, not the lower part. Okay. So that means this could be arabinose where there is OH on the same side. This could be arabinose on the opposite side. Here, this is on the left, this is on the right. That is the third possibility. And the fourth possibility is both these two on the left side. So which one is correct? Which one is correct? So now, remember one reaction that I told you, that these aldehydes on bromine water, these molecules give only the oxidation of the aldehyde group. CH2H remain intact. But if you add nitric acid, HNO3, then what happens? This will be oxidized and that will be oxidized. Okay, so you will get CO2H and in this chain and SCO2H. Okay, and then this OHs. Okay, now the result is that if you take minus arabinose and you oxidize with nitric acid, you get an optically active dicarboxylic acid. You get an optically active dicarboxylic acid. Okay, now suppose arabinose has this structure. This OH is on the right. This OH is on the right. This weight is on the right because Fisher assumed that this is the D configuration. Okay. So if this is the structure of arabinose, nitric acid oxidation, which oxidizes this as well as this, will lead to what? Optically active or optically inactive acid, dicarboxylic acid. If this is the structure. Remember, this will be CO2H. This will be CO2H. And then these three. So will it lead to optically active or inactive acid? If this is the structure. Is it optically active? Tell any one of you, please. What happened?
The optically active.
Is it optically active or not? For this, you just see whether there is any plane of symmetry present or not. Is it optically active? Or not?
The inactivity.
Prachi says inactive. Why it is inactive? Because of what? You have to say why.
Yeah,
Why
because it is a meso compound.
Yeah, that is true. Why this is the meso compound? Because it has got a plane of symmetry. See, ultimately you have to come to the final answer. It is a meso compound, which is same that you said it is optically inactive. But my question is why it is optically inactive or why it is a meso compound? Because it has got a plane of symmetry passing through this, right? So this cannot be structure of minus arabinose. That is clear. Okay. Now go back to all these four possibilities of D minus arabinose, all these four structures. So this structure is ruled out because dicarboxylic acid will be optically inactive, but the result is that it gives optically active dicarboxylic acid. What about this one? Second one, in this case number 10. What about this one? Does this lead to optically active acid or inactive acid? Put the CO2H here and the CO2H here and see whether the plane of symmetry is there or not. Plane of symmetry will not be there because this wedge is here and that wedge is there, right? So there is no plane of symmetry. What about here? You put carboxy here, you put carboxy, and now you're again the plane of symmetry is back because this wedge and this wedge are on the same side. And in this structure, again, there is no plane of symmetry. So this nitric acid oxidation ruled out two structures. These cannot be the structure of D-arabinose. Is it clear to everybody? But these two, out of these two, one is D minus arabinose. Okay. If you look at both the structures, you see this actually the wedge at the C2 is on the left and wedge at the C5, C2, C3, C4. At C4 is on the right in both the structures. What is not clear at this moment is the configuration of these three carbon, 1, 2, 3. So you can write a partial structure. You can write a partial structure of arabinose. What is the partial structure of arabinose? CHO, OH. You don't know what is here. You know what is here, OH, CH2H. So this is the partial structure of this. You should not write H. Is it clear up to this point? This is the partial structure of arabinose. So not clear yet, what is arabinose? Then, because Fisher thought that in order to prove the structure of glucose, you have to actually go down and start looking at building the structure of or confirming the structure of the lower homologues like aldopentose. So he started with an aldopentose, arabinose, and he found that arabinose on oxidation gives an optically active dicarboxylic acid. So that gives him two choices, and he could not write the structure of the only ambiguity is here 4, 5, and 3. We don't know what it is. Okay. Then, so this is the partial structure that is written, arabinose. Now they did one reaction, okay, on this Fisher. The reaction is HCN. Reaction is with hydrocyanic acid. What does it do? HCN, we know HCN adds to aldehyde, and the aldehyde becomes CHOH, CN, okay, cyanohydrin. And the remaining part stays there. This you don't know. This you know. This is CH2H. So you add HCN to minus arabinose. Okay. My question is, first of all, how many cyanohydrins you will get? How many cyanohydrins? Can anybody tell? I started with this compound. I added HCN. This is converted to CHOHCN, and that is what is called cyanohydrin. My question is, how many cyanohydrins you will get? How many cyanohydrins? Quickly. What is this carbon? Why you are not answering? This carbon is again a new asymmetric center, new stereogenic center. Okay. So there are two possible structures. See, this carbon is that carbon. After HCN, you can reduce HCN by reagents which are actually, I told you, Kiliani-Fisher, see, you make it an acid to lactone, and then hydrolyze the lactone. So that will give you, actually not hydrolyze, reduce the lactone. Let me see, it was there earlier. Last time I showed you. Didn't I show you? Aldopentose, Kiliani-Fisher, C3. What was that? Maybe HCN, H plus, it was just maybe not, just a quick. How to convert a cyanide into aldehyde? How to convert a cyanide into aldehyde? We were there. No, where were we? Just a second. We were here. Okay. I think let me repeat the whole thing. Huh? This. So where is the starting point? The starting point was again. I start. Huh? It started with arabinose. D minus arabinose was there in Fisher's hand. Okay. So Fisher assumed that it has got this structure. And then he didn't know what are the structures at these carbons. Okay. But what he did that he oxidized it with nitric acid. So this is D minus arabinose. He oxidized it with nitric acid, HNO3. And that oxidizes it to CO2H and CO2H. This will be OH, that will be OH, and this, he does not know. But from these optically active, because this is optically active, so immediately you can say that this OH at C2, 1, 2, has to be on the left side, because if it is on the right side, it creates a plane of symmetry. So this should be the partial structure of D minus arabinose. Okay, now you write this, you don't know what is here, 3, 4, 5. Now you, not this one, sorry. Now you add HCl to this. So you know what is the structure of arabinose then? This. 1, 2. Now you add HCl to it. So if you add HCl, this carbon becomes another chiral center. So this carbon becomes another chiral center. So you get a cyanide OH, cyanohydrin. Actually, this was the earlier number 1 carbon. Now, because of the cyanide, this is 1, this is 2, and 2 has become 3, 3 has become 4. So 3 you don't, means 4 you don't know the structure, and then this is CH2OH, you have already assumed, and this is CH2OH. You try to understand. This is CHO, so that becomes CHOH and CN. So that is what is written like this. So this carbon earlier was the number 1 carbon, but now because of the cyanide, you put this as 1. Okay, and this is 2, this is 3, this is 4. So the 3 has become 4, which is indeterminable, and then 5 and 6. Okay, so how many then you will get? This is cyanohydrin. So you must be getting 2 cyanohydrins. Another one is OH on the right, another is OH on the left. Because both possibilities are there. When you generate a stereogenic center, both RS are possible. So OH on the right and OH on the left. So this is OH, 4 you don't know, this you know, OH. That's all. So 1, 2, 3, 4, 5, 6. So now suppose this is A, this is B. So 2 cyanohydrins. What is their relationship? The 2 cyanohydrins, they are diastereomers because their configuration at one center is different. All others are same. Sometimes configuration at one center different means they are also called epimers. Epimers means their configuration at a particular center is different. So they are called epimers. But in general, you can call epimers are also diastereomers because diastereomers are compounds which are not mirror images. Okay, so they are, but they have a special class now, epimers. C2, there is a change. Okay, now you do a reaction which is hydrolysis. They hydrolyze by, I think, barium hydroxide and then sodium amalgam. What it does, it actually converted the CNO into CHO. So CN is converted into CHO. So you write the structure, what is coming from A. So OH, H, then OH, H, then you don't know, then you know OH, H, then you know CH2OH. So this is 1, 1, 2, 3, 4, 5, 6. And the other one is CHO, OH on the left side at 2. This is known, OH on the left side. This one is not known. This is known, OH. This is H. This is CH2H. Okay. So 1, 2, 3, 4, 5, 6. Okay. So what he found, so this is what these are. These are aldohexoses. So what you have done, an aldopentose, like D-arabinose, aldopentose is converted into what? An aldohexose. So it is called stepping up of carbohydrate, of monosaccharides, basically. That means you take an aldopentose, you go to an aldohexose. Or if you take an aldotetrose, all this can be done. You can go to an aldopentose. Only problem with this is that you get two isomers. You get two compounds because you are generating a new stereochemistry. So you get two compounds. This is what is called Killian-Fischer synthesis. Killian-Fischer synthesis. Okay. Now two compounds, these are aldohexoses. So what Fischer found that one of them is glucose, D plus glucose. And another one is D, I think plus, let's see, that is always, that confuses. Which one is plus, which one is plus glucose? This is fructose, so don't want fructose. The other one is mannose. Mannose, bromine water is, does it say anything? This is the Killian-Fischer. They don't say the name, the rotation. D-arabinose on oxidation, good. Dicarboxylic acid, that we have said. Then further oxidation. Where is that? This is okay, that is okay, that is okay, that is okay. This is okay. Suddenly came into the picture. Oh, we are actually going back. Maybe a little bit further it will be. Both are plus, D plus minus. Okay, because if I give minus, then that does not make sense. It is the L minus then we are talking about. That's why I am so concerned whether it is writing the right structure or not. Okay, so basically what we are saying that we have partial structure of arabinose, that is one. And then after arabinose, if we do a step up, that means Killian-Fischer reaction, we get two compounds. One is glucose, D-glucose, D plus, another is D plus mannose. Okay, we'll get two compounds. So from this, so D plus glucose and D plus mannose. These two are obtained by what? By Killian-Fischer synthesis of D minus arabinose. Okay. What is the structure of arabinose? I think this we discussed partial structure. Then we said that Killian-Fischer gave these two. Now, if you again oxidize this with nitric acid, remember arabinose structure, we could not We know that arabinose structure is something like this, which we don't know this. We know this. This is what is arabinose. What is the structure of glucose or mannose? We also don't know fully. What we know is that one of them is glucose and one, this is not known. This is known. This is known. This is the Killian-Fisher product. Okay. One Killian-Fisher product. The other Killian-Fisher product is this one. Wage. This we don't know. Why this is, we don't know this because it is coming from arabinose. That's why arabinose, it was not known. So you don't know the configuration of these. If you number it, as I said, this is 1, 2, 3, 4, 5. In arabinose, the C3 configuration is not known. In glucose, this is 1. This is coming from the cyanide. So this is 1, 2. Actually, this 2 is actually 1 for arabinose. So this 3 is actually 2 for arabinose. That is known. 4 is 3 for arabinose. That is unknown. 5 is 4 for arabinose. That is known. And this is 6. So this is how the numbering goes. And it was known that arabinose on Killian-Fisher synthesis gives D plus glucose and D plus mannose. What does it indicate? It indicates that D-glucose, C3, C4, C5, so this part and this part must be same for both mannose and glucose, because otherwise how I got glucose and mannose when this is differing only at this center. So the rest part of the molecule must be same. So I can say D plus and D minus mannose, D plus glucose and D minus mannose are C2 epimers. See how actually Fisher is slowly converging into the problem. First, he had one difficulty, that what is the configuration of this? If he knew the configuration of this, he could have written the configuration at these two centers. But difficulty is that which one is glucose, which one is mannose? That you don't know here. One is glucose, one is mannose. Okay. Now, but it is clear that mannose and glucose are intimately tied together. They are only C2 epimeric at C2. Other portion must be identical. Otherwise, how are they same? Okay. Next observation. He took this to, he didn't know which one is glucose, which one is mannose. Either this is glucose or this is mannose, or if this is not mannose, this is glucose. He does not know which one is which, but he could separate these two. And he separated these two. Suppose this is X molecule and this is Y molecule. So he took X and Y and did one reaction. X and Y separately. Put nitric acid. Again, the same reaction. What nitric acid does? Nitric acid converts this into acid and this into acid. So let us draw the two acids. COOH, then OH. Let us drop the hydrogens for the time being. OH. This we don't know. OH. Then CH2H. Okay, this is from X. And this from Y, what comes out? OH here, CO2H here. This is CO2H, sorry. CO2H. Dicarboxylic acid. And then the last, this is CO2H. So this is OH. Then this is OH. Right? Then you don't know what it is. And finally, you have, this is OH. Any problem up till now? So this is the situation that upon oxidation of nitric acid, he got these two carboxylic acids and he found that both are optically active. Both are optically active. What does it indicate? It indicates, oh, where was that which I don't, 1, 2, 3, I should have written this. This is not known and this is not known, okay? Now, both the carboxylic, dicarboxylic acids are optically active. Listen carefully. That means that now I had two possibilities. I can put wedge here or I can put wedge here. Let's see if the wedge is on the right side, does it really give optically active carboxylic acids in both the occasions or not? If the wedge is on this side, then you have a structure like this. Maybe the next slide it will be better. If the again a little bit bigger, so what is happening? I have two structures, wedge, wedge. This I don't know. This I know, wedge. This I know, wedge. Another structure is COOH. This is H, carboxylic acid. This is also carboxylic acid. And now this was on the right side. This was on the left side. This we don't know. This is on the right side. Okay. Oxidation gives optically active acids. That means if you are if you apply your brain, that means that the configuration of this, the wedge has to be on the left. The wedge has to be on the right. Sorry, the wedge has to be on the right. Why is that? Both are optically active, right? So if the wedge is on the left, then you look at this structure. This would have been not a problem. This would have been optically active because there will be no plane of symmetry. But if the wedge is on the left, that means this one, you will have a plane of symmetry between the two. So the wedge cannot be on the left at this center because one of them becomes optically inactive. However, if the wedge is on the right, then both are actually optically active. This is argument is okay for you, or should I repeat? Isolation of Acha, okay. See what I'm saying, you know that this glucose and mannose gives optically active dicarboxylic acids. Okay. And you know their part structure. The part structure. And from the part structure, you try to draw this is one compound. This structure, stereochemistry, you don't know. This you know, this you know. Now the part structures are like this. This is on the right side. This is on the left side. This you don't know. This is known. CH2, sorry, CO2H. Now you have options here. Suppose I think that the wedge, there are two possibilities. Either the wedge is on the right side. Suppose it is on the right side, I think. So I put on the right side, let's see, on both. And whether both the carboxylic acids are optically active or not. So this is the situation. Now, in both the cases, you see there is no plane of symmetry. No symmetry, no symmetry. Is that okay? And if you, what a minute. If you, got changed. Where was that? Yes. So I put weight on the right and I see both give optically active acid. Now I put the weight on the left and see what is the result. So erase this, erase that part, erase this part. I put weight on the left. So these are my possibilities. So put the weight on the left. Put the weight on the left. And this put hydrogen, put hydrogen, put hydrogen. The problem is this is okay. This will give, this is optically active, no plane of symmetry. Here there is a plane of symmetry. Here you have a plane of symmetry. So the very fact that both of them give optically active acid rules out that this weight cannot be on the left. Now you understood. That means glucose and mannose has this structure. We still don't know which one is glucose, which one is mannose, but glucose and mannose have this structure. And in arabinose, it must be the weight which is on the right side. It immediately proves the structure of arabinose. Is it? I think it is okay. Upon oxidation of nitric acid, both plus glucose and mannose yield dicarboxylic acids that are optically active. This means that the weight at C4 is on the right. They just said it in the book. I just explained to you. This means that the weight in arabinose was again, I repeat, this was arabinose. Everything was known, only the C3. But this experiment that upon upgradation and then further oxidation gives optically active acid means this weight has to be on the right side, cannot be on the left side. Okay, so arabinose structure is now fixed. This is what is arabinose. So the first carbohydrate structure which is known was D minus arabinose. Okay. However, people, because we are more interested in glucose, so next attention was that then what is glucose? Because one of them, yes, one of them was one of them must be glucose, another must be mannose. But which one is which? That was a big issue. Which one is which? There was no shortcut, but it was just sheer luck of Emil Fischer. Is that at that time, aldohexose, how many aldohexoses are possible? How many? How many aldohexoses are possible in nature? Can anyone tell me? Prachi? How many aldohexoses are possible in nature?
16.
16, yes, correct. And they can exist in DL pairs. So 8 DL pairs. Like there will be 2 forms of glucose. And then there will be 2 forms of mannose. They have different names. Glucose is one, mannose is one, galactose is one, glucose is one. I also forget all the names. But some of 8 names are there. And both are, all these can exhibit in DL forms, exist in DL forms. Okay. So there are, out of that, at that time when Fischer was working, what was known was glucose, isolated, glucose, mannose, which mannose? Plus mannose, plus glucose. And another compound was known at that time, that is called glucose. Okay, glucose is another aldohexose, different. Okay, but this glucose helped to identify the configuration of mannose and glucose. How? See, again, I write what is the possibility that this is either this is glucose or this is glucose. Okay, or this is mannose or this is mannose. Okay, now listen very carefully. This is actually a little complicated. When I remember also during my undergraduate days. Listen very carefully. Again, I write the two possible structures of glucose and mannose. One structure is this. Another structure is which is on the left side. Okay, now the question, what is our problem? Which one is glucose? Which one is mannose? Okay, we don't know, or Fisher didn't know. At that time, plus glucose was isolated, was known, plus glucose. And interestingly, when plus glucose was oxidized with nitric acid, it gave a dicarboxylic acid, same as that obtained from D plus glucose. Not from mannose. So this glucose, a plus glucose on oxidation, gave a dicarboxylic acid, which is the same as that obtained from D glucose. Now, suppose this is D glucose. Suppose if this is D glucose, then what is the dicarboxylic acid that you get? CO2H, which H, which H, which H, and then 1, 2, 3, 4, OH, and then CO2H. So this is the dicarboxylic acid that you get from, if this is glucose, if this is glucose. If this is glucose, then the dicarboxylic acid that you get is this. OH, 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 CO2H, H, 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 H. Okay, now because glucose gives the same dicarboxylic acid as glucose, so if this is glucose, that means your, see, this CO2H came from CHO. So glucose must be, how come they give the same dicarboxylic acid unless you think that this was CHO in case of glucose, and in glucose, they should be interchanging each other. Means if this is glucose, then glucose should be just inverted structure. CH2OH on the top, and the rest part is same, OH, H. This is also another thing you should, with conceptual thing. See, the other part should be same, and this should be CHO. If this is glucose, then they will, if this is glucose, then glucose and glucose will give the same dicarboxylic acid. Okay. And if this is glucose, then glucose should be CH2OH, because the middle part has to be same. Otherwise, how come they give the same dicarboxylic acid? So the middle part remains the same, OH, 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 and this is CHO. Is that clear? If this is glucose, structure say E, then structure B should be glucose. If structure C is glucose, then structure D should be glucose. Up to this point is clear or not? Because your reaction takes place only at this point and that point, does not disturb the middle portion. So middle portion has to be same for glucose and glucose. Okay. Now, can you tell me whether A and B are same structure or different structure? Or C and D are same structure or different structure? Who can tell me? If you are, again, I write two structures like say C and D. C is CHO here, OH here, OH here, OH here, OH here. H2H, H, 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 H. And I said interchange the positions of the two, keeping the others intact. CH2H on the top and OH, 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 H, 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 C, H, O. What about these two structures? Are they same or different? That is the last part of today. If you can give answer, you will get better grade. Who can give answer? Let's see. Name. Are these two structures same or not? Yes, there is a competition now. Shreya, are these two structures same? Nipun, Shivam, Siddharth, Abhijit. You have to give argument also. Means only same, there is a 50-50 chance. Are they same or different? Again, go back to the structures. Show the structures. These two structures we are talking about. These two structures are the same. How do you determine two structures same or not? Fisher projection. Why are you having difficulty? You are having difficulty because at the top CHO, here the top bottom is CH2H, here the top bottom is CHO, top is CH2H. So what you can do in Fisher projection, you can turn it up 180-degree in plane rotation. You know that? 180-degree in plane rotation. So if you suppose this is your M structure, this is your N structure. Suppose I do 180-degree rotation on N, then the structure becomes what? This is allowed. This does not change the structure. So CHO will be on the top. This OH was on the right. So after 180-degree, it comes here. After 180-degree, this was on the right, it will come to the left. After 180-degree, this OH was on the left, so that will come to the right. After 180-degree, this was on the left, so that will come to the right. And this will be CH2H, H, 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 H. Now tell me, are these two structures same or not? Otherwise, they both are mirror. M, my question is M and this new, say, P, are they same or not? Why do you say mirror images? I could see same. OH, 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 then left OH, then left OH, then OH and CHO. This N, I have done 180-degree in plane rotation. That is allowed. I put the CHO on the top, CH2H at the bottom. While doing so, the right hand groups will go to the left hand, the left hand groups will go to the right hand. That's what I did. Now my question is relationship between M and P. They are same. Is it clear? Not clear, or clear?
Yes, sir.
It's clear now. Huh? Go back and then again do the same exercise on the other structure. What is the other structure? The other structure is this one, OH on the right. Here you have started OH on the left. We have started with the C structure. Actually, this is C. You can do on the C also, on the other structure, that is AB. AB. I will do AB. CHO, OH on the right, H on the left, OH on the left, H, OH, OH, CH2H. Okay, H. Now what you do, you interchange the position of these two. So CH2, this is CH2H and this is CHO. So keeping other things intact. Why is that? Because I told you that dicarboxylic acid does not change the internal structure. But the very fact that glucose and glucose give the same dicarboxylic acid, that means there is an interchange between these two groups, nothing else. Only thing that by interchanging which gives new structure. So this is the other structure you have interchanged now. Now if you do 180-degree in plane rotation, in plane, what will be the structure? This CH2H will be back to the down. This CH will be at the top. This OH carbon that will be at the top now. It was on the right, that will come to the left. This right will come to the left. Then this left will come to the right. And this right will come to the left. Okay. So now the question is, suppose this is K, this is X, this is Y. Now the question is, X I have changed by rotation, just by rotation, not changed, 180-degree in plane rotation. Is K equal to Y or not? Is K equal to Y? Is K equal to Y or not? That is the big question. Actually, they are not. If you look at the structure, this wedge is on the right, that wedge is on the left. This wedge is on the left, that is okay. Then this is right. So there is a change here. And there is a change here. So they are not the same structure. Unlike the previous case, they are the same. M and P are same structures. So by interchanging the groups, you see, interchange allows only creation of a new structure in A. Interchange does not allow creation of a new structure in C. So if that be the case, A must be glucose and C must be mannose. The last word, was it okay? What did I say? That again, if you want, there are 3 compounds plus glucose, D mannose, and plus glucose. What was found that glucose and glucose give the same dicarboxylic acid. So that means that their structures are closely related. The middle part is the same. Only change is at these positions. In glucose, CHO is at the top, CH2OH is at the bottom, and you can get glucose by changing this to CH2OH and this is to CHO. So what we did, we had 2 structures of mannose and glucose, and we did this change, and we found that in one of the structure, you get a new structure by this interchange. Another structure does not give the new structure. So one which gives new structure must be glucose, and one which does not give the new structure cannot be glucose. That is mannose. Okay. And the new structure that you generate must be glucose. So the structure of glucose, glucose, mannose, they are all done in one step by Fischer. In one single step, everything was proven. So basically 3 experiments. He started from arabinose. Arabinose gave optically active carboxylic acids, dicarboxylic acid. From these observations, he could write the structure of arabinose, except one center remained. Then Kiliani-Fischer, it gave mannose and glucose. Both gave optically active carboxylic acid. So that fixes the structure of arabinose immediately. And then the question of which one is glucose, which one is glucose, mannose, that depended on the oxidation product of glucose was matching with that of glucose. So you can now write the 3 structures. This is what is glucose. Somehow you have to memorize this. Right, left, right, something, some mnemonic you can do. So this is D plus glucose. This is mannose, which is on the left. H, all parts are same, only the top part. So this is D plus mannose. So what is then glucose? This is glucose. What is glucose? You have to interchange these two. So structure of glucose is CH2H, CHO, these, keeping these all the same, wage. Any question? This is plus glucose. Any question? Any understanding problem? If you want, I can write a short write-up to clarify this thing, that how it was obtained, like what I means in a very simplified manner, that what experiments can prove the structures. Actually, ultimately had proved the structures. Okay. My final question before I leave, that who actually means which experiment established the structure that this is on the right side? No experiment, right? It was assumed that all these products, arabinose, glucose, they have deconfiguration. So this was the assumption of Fischer, Emil Fischer. And Emil Fischer argued that ultimately later on, after his death, if it is found that this weight is actually on the left, then all the structures that he wrote for these different natural compounds will be just the mirror image of this. Okay. Fortunately, what happened later on? X-ray crystallography proved that this is whatever he assumed was correct. So everything remained intact. Okay. The question is now, what is the configuration of glucose? Is it D glucose or is it L glucose? Is it D glucose or is it L glucose? What happened? Tell me whether it is D glucose or L glucose. Quick. What is the problem? It is not written in the right fashion in Fisher projection. No? In Fisher projection, the CHO should be at the top and CH2OH should be at the bottom.
Sir, it is L.
It is L. Is it? Yes, so you have done that 180-degree rotation. So if you do 180-degree rotation, what will happen? Your this wedge actually will. So 180-degree rotation now will give this structure. CHO will be at the top, and then this is on the right, so that will go to the left. This is on the right, that will go to the left. This is on the left, that will go to the right. And this is on the right, that will go to the left. And this is CH2OH. Okay. So this is L plus glucose. So basically by one experiment, so many things were discovered. But he had that risk with his D and L assumption, whether correct or not. But fortune favored the brave. So Fisher was rightly awarded the Nobel Prize for this structure elucidation at that time. Okay. There may be several types of problems that can be generated from this. If you want, I can write up this, whatever I told you today, and then send to you. That will be better. This is little complicated. Nothing. It is just stereochemistry, stereochemical jugglery. That is what is needed, and conception, and that will solve the whole carbohydrate chemistry. Okay. So I think now almost I have to leave now. Sorry for that, but you may be happy that the classes of will definitely compensate for this. We had last time we didn't take half an hour. This time also we are not taking half an hour. Hopefully you are okay with that. No sound. Hopefully you are okay with that.
Yes.
Because there is some actually lecture right now by a foreign visitor. So I have to go there. Okay then.
Thank you, sir.
For sure. So we'll stop here. What happened? Where are those cursors? Escape. Escape. Yes. And show it. Yes. Okay, have a nice time.
Thank you, sir.
Read more.